Hello, so this is a revision video for AP Chemistry 8.5, Acid-Base Titrations. A titration is an analytical technique used to determine the concentration of an unknown solution, the analyte, by reacting it with a solution of known concentration, the titrant. Titrations are particularly useful when a reaction occurs completely and predictably between the two substances, for example, an acid-base reaction. The equivalence point in a titration occurs when the amount of titrant added exactly reacts with all of the analyte present at the start. The moles of titrant and analyte have been mixed in the correct stoichiometric ratio shown with the balanced reaction equation. For example, a simple 1-to-1 ratio for an acid-base reaction is HA plus O minus goes to form A minus plus H2O. The equivalence point is reached here when the moles of OH minus added equals the moles of HA in the starting solution. The endpoint in a titration occurs when enough titrant has been added to cause an observable color change, by an indicator in the solution changing color. This is used to signify that the equivalence point has been reached in the titration. For example, the indicator phenolphthalein turns pink in alkaline solution. So in a titration between a strong acid and strong base, the end point is reached when the indicator permanently changes color to a faint pink color. Notice here that the end point and equivalence point in a titration aren't actually the same thing, but we want them to occur at the same point. So an indicator should be chosen that will have an end point that should match the equivalence point for the given reaction. So for an acid-base titration, the pH that will cause an indicator to change color should be the same pH achieved when the acid and base react together perfectly. Exam tip here: when using titration-based data, always write the balanced chemical equation first to identify the correct molar ratio between titrant and analyte. Keep all units consistent, especially volumes used, and be precise when reading from your buret. You should always read the buret from eye level and always make sure the bottom of the meniscus is on the line being measured, the meniscus being the curved shape of water in a narrow container. A titration curve is a graph that shows how the pH of the solution changes during the titration. In other words, how the pH changes as more titrant gets added. A titration curve has several key features. The initial pH of the starting solution is shown by the intercept of the y-axis. The steep region indicates a rapid change in pH that occurs around the equivalence point, and the final pH is the pH of the solution after excess titrant has been added. You should be aware of the different shapes of titration curves for acids and bases. A strong acid and strong base has an initial low pH because it's a strong acid to start with, and the equivalence point should be around pH 7 because it will be a neutral salt that gets formed, and the final pH will be high because an excess of strong base added will give a high pH of the final solution. For a weak acid with a strong base, the initial pH will be slightly higher because a solution of weak acid will have a higher pH than a solution of a strong acid. There is also something called the buffering zone. This occurs when there is a mixture of both the weak acid HA and its conjugate base A- in the solution. This forms a simple buffer system. So as more base gets added to the acid, the pH is buffered and doesn't change very much, meaning the graph looks a little bit flat during the buffering zone. The equivalence point will be slightly higher than pH 7 because the salt that gets formed is basic and will react with water molecules to produce hydroxide ions, meaning when the weak acid and strong base have completely reacted together, the solution won't actually be neutral because the salt that gets formed will actually react with water molecules to release more hydroxide ions. Again, the final pH will be high due to the excess of strong base. For a weak base and strong acid, it's a mirror image of a weak acid titration, but this time you start with a low pH because it's a strong acid, and the equivalence point will be lower than pH 7. Because at the equivalence point, the salt that gets formed will actually be acidic and will react in solution to release H+ ions, lowering the pH. And finally, for a weak acid and a weak base, the titration curve isn't very clear at all, and there is no sharp region where the equivalence point occurs. Because of this, weak acid and weak base reactions can't be used in titrations. The reaction doesn't actually go to completion. Polyprotic acids are able to donate more than one H+ ion in reactions. This means there are multiple equivalence points in their titration curves, one for each proton. Each steep region in the titration curve represents one H+ ion neutralization. For example, for a diprotic acid, H2A, with a strong base, the titration curve would show two sharp vertical sections. The first one will be for the acid reacting with hydroxide ions to produce Ha- and H2O, and then the second one will be for Ha- reacting with more OH- ions to form A- and H2O. pKa values can be estimated from half-equivalence point between each stage, because at the half-equivalence point, the concentration of Ha and A- are the same.